This is the third part of our discussion on complex exponential function. So far, we have defined them and we discussed some basic properties. Now, in this part, we are going to see or discuss the range of exponential function. Okay, so in particular, we will be interested in whether this function is one-to-one, whether this function is onto, etc., etc. Okay, now for very simple reasons, this function is not onto. Okay, so the reason is that over here we have this exponential function, and this exponential function cannot be 0 for any real number x. And similarly, this cosine y and sine y, they cannot be 0 at the same value of y. That's why this expression cannot be equal to 0. So the output of this complex exponential function can never be 0. So that's why we can say that it is not an onto function. Okay, so moving on to the next property, whether this function is one-to-one or not. So in the previous module, we observed an example. Okay, in that example, we see that in a very simple way that this function is not one-to-one function. Now we are going to explore further why it is not one-to-one and further properties that will affect, okay, so on the calculations of exponential function. So given this exponential function, take this to be z plane and take this to be w plane. Now we want to see whether this is one-to-one function or not. Okay, so as I said earlier, as I told you earlier, that it is not a one-to-one function, but what is this repetition? Okay, so for example, if there are two values, let's call them z1 and z2, and both of these values have equal output. Okay, so if z1 and z2 both have equal output under this exponential function, okay, so this is going to be the output, then what is the relationship between z1 and z2? Okay, so we have seen that there is a relationship between z1 and z2 as well. So z1 is equal to z2 plus 2n pi. Okay, so for some n. For some n. So that's what we have seen so far. Okay, now we want to explore further. Okay, so given this z to be equal to x plus iota y and w is equal to e raised to power z. Okay, so this is the output which is equal to e raised to power x plus iota y. Now if we say that this output, okay, so w is basically equal to rho e raised to power iota phi. Okay, so if we use this polar coordinates in the w plane as well, then z is equal to e raised to power z, w is equal to e raised to power z. Basically this becomes e raised to power x plus iota y is equal to rho e raised to power iota phi. Okay, so now we know that as we have discussed earlier, that e raised to power z1 is equal to e raised to power z2 if and only if there is a difference between z1 and z2, which is basically a difference in the imaginary part only, and the number is basically fixed, and it is basically 2n pi for some integer n. Okay, so using this property, we can say that this e raised to power x is equal to rho. Okay, because this is just the real part, and e raised to power iota y is equal to e raised to power, okay, iota y is equal to e raised to power iota phi. Now using this observation fact, in fact, so using this fact, we can this implies that there is a difference between y and phi, and iota y is equal to iota phi plus iota 2n pi. Okay, so we can just cancel out this iota, and this becomes x is equal to log of this rho, and of course this whole situation is real. Okay, so these are this is real exponential function, this is real logarithm, natural logarithm, and over here this y is also real, phi is real, 2n pi is real. Okay, so because we just cancel out this iota, so there is a relation between y and phi now. Okay, so precisely we have the following situation now, because this rho is basically the modulus of this w. Okay, so that's why we have the following situation: x is equal to the natural log of modulus of w, and y is equal to phi plus 2n pi. Okay, and this becomes, so if z is equal to x plus iota y, then putting the value of x is equal to log of modulus of y, and y is equal to 5 plus 2 and pi. So our expression for z becomes log of modulus of w plus iota 5 plus 2 and pi. Okay, so moving on. So this, if this phi is basically the argument of w, then this expression becomes the phi iota argument of w, the principal argument or the argument of w, plus 2 and pi. So this is basically the value of z. Okay, so these are all values in the z plane. Okay, so in the z plane, these are the values of complex numbers, such that when we take the image of these values under the exponential map, the output is going to be equal to the same number w. So these are infinitely many numbers, right? So here n varies over the set of integers. So these are infinitely many complex numbers in the z plane, such that when we apply the exponential map on all of these complex numbers, then we are getting the same number w. Okay, so in other words, now what can we calculate using this expression? So given a complex number in the w plane, we can now in fact calculate the set of all numbers, such that these numbers are mapped onto the same number from this w plane. And of course, this expression says that there are going to be infinitely many numbers in the z plane which are mapped onto this w. Okay, so that's why this expression is useful. Okay, so now we are basically able to find a structure between the functional values. Okay, and the fact that if we have a number over here, okay, so let's call it z, then if this number is let's say the imaginary part is alpha, and if this number is at a distance of 2 pi along this imaginary axis, so in other words, if the next number is basically over here, which is basically has the same real part, but the imaginary part is has a difference of 2 pi, and similarly if we write down other number z2, which is at a imaginary part is alpha plus 4 pi, and up to so on. Okay, so all of these numbers, so they are going to be mapped onto the same number. Okay, so all of these infinitely many numbers, so they are going to be mapped onto the same number, let's call it w. Okay, and using our previous discussion, given this w, we can in fact find out all of these complex numbers in the z plane which are mapped onto w. Okay, so that's one thing that we have achieved. Okay, now the next observation. So the next observation is there is a kind of periodicity in the output values. Okay, so for example, if we take this z, and let's say this imaginary part is alpha, and if we take alpha plus 2 pi and this complex number, then since these are the same values, so there is going to be repetition. Okay, so for example, if we take this number over here, then its output is going to be the same as this number. Okay, so moving on to next number, so if we take this number, then the output is going to be equal to the output of this number. So there is a kind of periodic behavior in the z plane. Okay, so that's why we can say that if we want to calculate the image of all of these values, so for example, from this point to this point, and not including this next red dot. Okay, so what is going to be the output of all of these values? Now remember, when we want to calculate the image under the exponential map, then the exponential map e raised to power z is equal to e raised to power x multiplied by cosine y plus iota sine y. So in other words, this real part, let's say this real part is over here, is let's call it a. Okay, so this real part decides basically the distance of the output from the origin, in other words the modulus of the output. Okay, and for all of these values on this green line segment, the real part is same. So that's why we can say that they are all, so the output of all of these complex numbers on this green line segment is going to be at the same distance from the origin. So in other words, they are going to be on the same circle. So let's say this is the value of e raised to power alpha. Okay, so this is the value of e raised to power alpha, sorry, a. Okay, so because we have taken this real part to be a, so e raised to power a is basically this is the distance from the origin. Okay. Now what about the imaginary part of these complex numbers? Now over here we can see that the real part is fixed, but the imaginary part is changing. Okay, and of course it's going to repeat its values after each 2 pi. Okay, now if we move from alpha to alpha plus 2 pi, then over here in this expression we can see that this is going to be the argument. Okay, so this is going to be the argument of the output, and from alpha to alpha plus 2 pi we are going to take one complete round. Okay, so because we will start from alpha and we will end up at alpha plus 2 pi, and after that this cosine y and sine y will repeat its value. So that's why what is going to be the output of this green line segment? It is going to be one circle, complete circle with the radius e raised to power a, and it is basically a circle because the value of the argument starts from alpha to alpha plus 2 pi, so it's a complete one cycle. Okay, so in particular if we have other examples, so now over here you can see that this brown line, so it will be mapped onto this brown circle, and this orange line is going to be mapped onto this orange circle. Okay, now these are the lines over which this the real part is basically the same, but the imaginary part is moving. Okay, what about the other way around? What about this red line? Okay, so now let's consider this red line. So on this red line we can see that the imaginary part is fixed, but the real part is changing. Okay, so as we have discussed that the real part is basically the modulus of the output. Okay, so in other words we can see that the modulus is changing, but the imaginary part is fixed, so that's why the argument of the output is going to be the same. Okay, so whenever we take any real number and calculate its exponential, so whenever we calculate e raised to power x, then it is always going to be a non-negative and non-zero real number. So that's why the output is going to be a line, basically half line starting from origin, and origin is not included because exponential function cannot be 0, so it is going to be this radial line, and origin is not included, and the angle is fixed because the imaginary part is fixed, but all the elements on this radial line are included because this real part is changing, okay, in the z plane. Okay, and similarly if we consider this green line, okay, so let's consider this line now. Okay, so once again the same observation, the imaginary part is fixed but the real part is changing, so that's why the output is going to be a radial line. Okay, so this radial line, and similarly this dotted green line, once again it is going to be a radial line, but what is going to be the relation between the output of this solid green line and this dotted green line? So what is going to be the relation between them? Now if we see the difference between their imaginary parts, then we can see that this line, so all of the points have imaginary part minus iota pi, and all of these points have imaginary part plus pi. Okay, so that's why the difference between the imaginary parts of these two lines, okay, so the points on this line have the same imaginary part, and the difference is going to be equal to 2 pi. Okay, so so that's why, okay, so we can say that, okay, so the point is this output is going to be the same, because we know that whenever there is a difference of 2 pi, then the values are going to be repeated. So that's why we can say that when we calculate the output of complex numbers, okay, so in this region, okay, so now this region is going to be important now. Okay, so this region, okay, consider this region, this strip, okay, so between minus pi and pi. So whenever we calculate the output of the complex numbers in this strip, then these are going to be somehow unique. Okay, so why they are going to be unique because the repetition will occur after this thing, because if there is no difference of 2 pi between the imaginary parts, there is not going to be any repetition. Okay, so in this strip, whenever we take any two complex numbers, then the difference between their imaginary parts is going to be less than 2 pi. Okay, because they are in the strip of width 2 pi. Okay, so that's why the output is always going to be unique, and there is not going to be any repetition. So that's why this strip is kind of important. So this strip is going to be known as the fundamental strip, because once again the width of this strip is basically 2 pi, and the repetition occurs. So the repetition means the output of two different complex number is going to be the same whenever the difference between their imaginary parts is 2 pi or some multiple of 2 pi. But this is not going to happen whenever we take two complex numbers in this strip, because the difference between their imaginary parts cannot be multiple of 2 pi, because the width of this strip is 2 pi. So that's why we have found a very important kind of subset of Z plane. Okay, so this subset has this property that this exponential function is one-to-one in this subset of the Z plane. Okay, so it has a special name, and it is known as the fundamental period strip, because above and below this strip there will be repetitions. Okay, so in other words, if we have Z is equal to e raised to power Z, e raised to power x plus iota y, then we have observed this thing, and in this observation, okay, so instead of taking 2 and pi, we just take argument of w. Okay, so basically we will be in this strip. So now let's consider this simple example where we want to calculate all values of Z which are mapped onto this complex number in the w plane. This complex number is -4, and we know that how to find these values by using this expression that we derived. So Z is equal to log of modulus of w. So remember, in this case w is -4 plus iota principal argument of w plus 2 and pi. Now this number -4 basically is somewhere over there on the real axis, and in this case we can see that the principal argument is 0. There is no angle, it's 0, and the modulus of -4 is 4. Once again can be calculated. So the output becomes log of 4 plus iota 2 and pi. So for all of these values, so the output is going to be -4. Okay, so we have used this expression that we derived from this module. Now we want to find the image under the complex exponential function of all of these numbers. Okay, so what are these numbers in the Z plane? So the real part x lies between 1 and 2. So let's say this is 1 and this is 2. So the real part lies between 1 and 2, but the imaginary part lies between -pi/4 to pi/4. So let's say this is -pi/4 and this is pi/4. So basically we are talking about all the numbers which are in this portion. Okay, so all of the numbers. So once again the real part lies between 1 and 2, and the imaginary part lies between -pi/4 to pi/4. Now we want to find out what is going to be the image of this region in the W plane under this complex exponential map. Now the point is the output of 1 is going to be e raised to power 1, and the output of 2 is going to be e raised to power 2. Okay, so let's say e is somewhere over there. Okay, and e raised to power 2 is, let's say, somewhere over there at a distance of e and e square. Okay, so the output of 1 is e and output of 2 is e square. So whatever output is going to be, it is going to be between these 2 points. Okay, so for very simple reason, because e raised to power 1 is less than or equal to e raised to power x less than or equal to e square whenever x lies between 2 and 1. And what about the argument of the output? What about their angles? Okay, so for very simple reason, which is -pi/4, is basically the argument of this complex number e raised to power x plus x minus iota pi/4, which is going to be equal to, which is less than or equal to argument of e raised to power x plus iota y, and x and y have the same condition as given in the set A, and this is going to be less than or equal to the principal argument of e raised to power x plus iota pi by 4, and which is of course going to be equal to pi by 4. So due to this reason, all of the elements in the output are basically, they have argument between minus pi by 4 and pi by 4. Okay, so all of these elements where y range from minus pi by 4 to pi by 4. So in other words, we can say that if this is pi by 4 and if this is minus pi by 4, then all of the output is going to be between these two radial lines and these two sectors of the circle. Okay, so in other words, this is going to be the output of this region. Okay, so this is basically E, this is E square, this is pi by 4, and this is minus pi by 4. Okay, so this is going to be the image of this region in the Z plane. So in this module, we discussed different properties of complex exponential function. In particular, we discussed whether it is one-to-one, whether it is onto or not. In fact, it is not an onto function, but apart from the element 0 in the W plane, all of the elements lie in the image of complex exponential function. This is the end of our discussion on complex exponential function.